Okay, yeah, thank you so much. Thanks to the organizers for bringing this wonderful group of people together. Thanks to the audience for sticking around for the last talk. It's kind of late, but so the main topic of today will be based on this paper, which is joint work with Alec, David, and Kamran. They're all in the audience, so please feel free to ask some questions. Okay, the motivation for this is very similar to the motivation for the workshop, which is that there's a really nice interplay between ideas from string theory and the Swampland program, and also data, cosmological data, recent cosmological data. So here, during Alec's talk, we heard a little bit about this UV consistency, UV consistency conditions that we get from string theory. And the picture we have in mind is something like this. So at the vertical axis here is energy or inverse distance, and the horizontal axes here are supposed to represent theory space. And at very low energy, theory space is vast, and there are many, many theories that look consistent at low energy. However, it turns out that in practice, most of this theory space cannot be reached if you start from something like string theory in the UV. At very short distance, if you start from something like string theory, you can only reach a very, very tiny fraction of this humongous theory space. And so there are non-trivial consistency conditions on theories at low energy that you can try to ask about. And this is a whole program. This is the Swampland program. So because the outcome of this program are statements about low energy physics, you can hope to connect these statements to experiment. And of course, this is an ambitious goal. Like we're going to try to learn something from string theory and then connect it to experiments at very, very long distance. But in this talk, I'm going to give you an example of how you may realize this goal. This will be a concrete example. We will get a model. We'll start from very general principles, and then we're going to get a model that you can test against data. It's predictive. And not just that, it turns out that it actually provides a really good fit, to current data. It's preferred over the lambda CDM paradigm, for instance. I will say as we go along, I will say a lot more about what conditions we're going to use. I will say more about the data that we're going to use. But basically, this is the motivation. So in some sense, this is a combination of the last few talks that we heard, the combination of the takeaways from Alec's talk, which is that there are consistency conditions from the UV, and that data is telling us about exciting things, about cosmology. Okay, the takeaway messages for today's talk will be the following. So just like we saw in Mustafa's talk, one of the takeaway messages is that there's evidence in data, at about 3 sigma level of new physics, perhaps in the form of dynamical dark energy, perhaps of something else. But actually, this evidence we're going to interpret in this talk as evidence supporting a really simple string-inspired model, which is simple in the sense that the dynamical dark energy is modeled by means of a scalar field with a really simple potential. It's just an exponential. So these sorts of things, we get always in string theory, and that the dark matter mass actually depends on the same scalar field, and the dependence is also exponential, which is also the thing that we always get in string theory. So this is a very simple model, and we're going to see that data actually has a preference for this model over lambda CDM at the same level as the CPL parameterization. Okay. But so not just this model, is not just preferred by data, but it also provides a physical explanation of this phantom behavior. So we saw that the equation of state parameter goes to values below -1. I will say a bit more about this later. But this model has the additional feature that it provides an explanation for this phantom behavior in terms of a physical model, and it has predictions. So it's testable in other experiments. For example, it predicts a fifth force in the dark sector that one can go out and look for in independent experiments from cosmology, and just astrophysical experiments. Okay, and yeah, please feel free to stop me at any time if you have any questions. Okay, so with this,
what's the mass of pi?
Sorry?
What is the
mass? It's Hubble. It's Hubble scale. It's rolling, yeah.
Is always the Hubble scale? Or is the Hubble scale
Today.
Hubble scale today?
Okay. Yeah, the Hubble scale today, yes. Okay. All right, so this was the motivation, and with this motivation, we're going to follow roughly this outline. So in the first part of the talk, I will review some of the theory. So I will tell you about the ADS distance conjecture, and then we're going to take this statement from the ADS distance conjecture and apply it to our universe. Then this will motivate a dark matter candidate, which I will describe in the context of this dark dimension scenario. And then we're going to to interpret recent data, which is BAO, supernovae, CMB, the same data sets that we saw in the previous talk, in the context of this dark dimension scenario. And then finally, I'm going to tell you about the results that we get and their implications. So in particular, phantom crossing, fifth forces, before I summarize and provide an outlook. Okay. So we'll start with the theory. I don't know if I'm blocking someone's view, but let's stand here. Okay. So to begin with, we'll talk about the distance conjecture. So here I'm just going to state these statements. And so the statement of the ADS, so the setup for the ADS distance conjecture is a theory coupled to quantum gravity. So either in de Sitter or in ADS space. So in particular, it has a non-zero cosmological constant that we're calling lambda. So this you should interpret as a dark energy density. Okay, so this doesn't strictly have to be a cosmological constant. It could also be a rolling dark energy density, just like we're going to have later. So in such a theory, the statement of this conjecture is that you can try to make the dark energy density small, but the cost of that is that there's a tower of particles that becomes light in the limit as the absolute value of lambda goes to 0. So if you try to make the dark energy density small, then there's an infinite series of particles like this one. So this vertical axis represents mass, and these horizontal lines are supposed to represent particles of different masses. In the limit where lambda goes to 0, all these particles become light, and the rate at which they become light is dictated by lambda itself. Okay, so it's lambda to some order 1 number alpha with an alpha is positive. Okay. This is the statement of this conjecture. I'm going to rephrase this, in some language that could be more familiar. So schematically, you can think of, we might have a theory that has that has gravity and a cosmological constant, plus potentially many other things, like the standard model or any other particle you want to include. And then this is an effective field theory, and you can ask, what happens if I try to take the limit where lambda is very, very small? This one here is actually m Planck to the 4. So everything here is written in Planck units. So you can try to take the limit where lambda is super small. In effective field theory, nothing really happens. You would just maybe omit this term. Okay, but what these UV consistency conditions from string theory are telling you is that it's not actually consistent to just omit this term. And the limit where lambda is small, you must actually include in your theory an infinite tower of particles with masses for each particle. It has a mass m sub n, and this m sub n is related to this lambda that you're trying to make small. Okay, so in the context of string theory, the limit of this theory always includes this tower of particles, and it's not possible to get rid of this. This is the statement of this of the ADS distance conjecture. Okay, so if you try to make lambda super small, you will get this infinite tower of particles in the theory. Okay, any questions about this? No?
What is the evidence for this for ADS?
Oh, for ADS, it's huh?
Probably you want to tell for people who are not in string theory, what's the evidence for?
Yeah, for ADS, so if you're trying to do ADS, then one way to construct ADS is you start from some 10-dimensional string theory, and you want to get like ADS 5, for example. So what you can do is you can compactify 5 of the dimensions on a sphere, and then the remaining 5 dimensions form an ADS space. But the curvature of the sphere is linked to the curvature of this ADS space. So taking lambda to 0 means you're taking the flat limit of the ADS space, which is also making the sphere very big. Okay, when the sphere is very big, these particles are the Kaluza-Klein modes on the sphere, and so this is, this is one of the pieces of evidence for AES. But the intuition is that there are always these extra dimensions that determine two things. They determine the cosmological constant, but they also determine the spectrum of particles. And it's not possible to make the cosmological constant small without doing something extreme to these extra dimensions. And then this extreme thing that you do to the extra dimensions will also make this collection of particles light.
Sure.
So yes, very light in the sense, yeah. Yeah, I mean, in the limit, so this is an asymptotic statement, really. This is a statement only about, yeah. Yeah. So this is, okay, other questions? Yeah, it's just there are internal dimensions that become large, for example, if you're trying to make the cosmological constant small. Good. Okay, so now the next step is we take this statement and then we apply it to our universe. Of course, in our universe, we measure the very, very small dark energy density, rho dark energy, which is the same thing as lambda that we were writing on the previous slide, is 10 to the minus 120 in units where m Planck is 1. And this number is super, super small, much smaller than 1. This is the smallest number we've ever measured. Good. As an energy scale, it's a milli-electron volt scale to the 4. Sorry? In Planck units. Oh.
Sorry, I'm joking. If you want smaller numbers, you can change your units.
No, yes. No, the smallest number we have ever measured in Planck units. In Planck. Yes, that's correct. Yeah, as an energy scale, it's just a milli-electron volt scale. And so because this number is so small and because of what we have seen on the previous slide, you could ask, could there be a tower of light particles in our universe whose spacing is set by this tiny number? And this question was actually asked in the original paper on the ADS distance conjecture. Good. It turns out that the answer is yes. There can actually be a very light tower of particles in our universe. So I won't have time to go through the details of the full argument. That will probably take another talk. But I'm going to give you a summary of what it is. But please feel free to ask me questions now or later. Right. So the upshot is that yes, our universe can have a tower of particles, and whose spacing is set by the cosmological constant value. So his spacing is set by the milli-electron volt scale. Okay. This tower, so most possibilities are actually ruled out. The possibility that is not ruled out is the case where this tower is a Kaluza-Klein tower that comes from one extra dimension. So if you have one large extra dimension, and we live on a brane like the standard model brane that's suspended in this extra dimension, then from the 4-dimensional, so this is a higher dimensional picture, but from the 4-dimensional point of view, you would think that there's just a standard model and then a tower of particles, just like what I was showing with the horizontal red lines. The masses of the mass of any end state in the tower is inversely proportional to the length of this extra dimension. So the fact that this is milli-electron volt spacing means that the length of this extra dimension is on the order of milli-electron volt inverse, which happens to be around the micron scale. Okay, so it's 10 microns. So this is a very large extra dimension, and if we were not stuck to the brane, you would actually be able to see it by means of a microscope. So this is super large. Okay. So this is the possibility that that's not ruled out by experiment. If you try to have multiple, large extra, you could ask about other things, but most of them are like either ruled out or borderline ruled out by experiment. Yeah, so this one seems fine. Okay, the particles of this tower are automatic. So we wrote a few papers. In one of these papers, we showed that the particles of this tower are actually automatically produced in the early universe. So you don't need to create any production mechanism. They're coupled to the standard model brane by gravity, and they are just produced in the early universe, and they can easily be the dark matter. So they could easily be the dark matter in our universe. So then this model actually ties together the nature of dark energy and dark matter. So in the context of this model, the reason we have dark matter is because the dark energy density is so small. So the smallness of the dark energy means that there's a tower of particles, and then you produce that tower in the early universe, and that shows up as dark matter in our universe. So this somehow unifies the nature of dark energy and dark matter. At least it ties it together, and in the sense that one is the consequence of the other. Okay, there are various experimental signatures. I really won't have time to talk about any of these, but please see Miguel's and Ignacio's talk. We also discussed many of them in these papers. So please come ask me later if you're interested in any of the experimental signatures. Any questions about this? Yes.
What's his sense the MEV spacing? Is it just something you add in by hand?
No, the MEV is from here.
No, because you want to explain the CC, but there's no UV reason for it to be for the large extra dimension to be MEV.
No, the MEV scale is set by this. Yeah.
No, I think he's probably. I think he's trying to see the connection between this and why is the mass of this tower has to do with lambda. I think he's asking that question. Why does that set the tower scale?
Why does this set? Well, I mean, the statement of the conjecture is that m is like lambda to some power. So you're asking why is the power a quarter? Maybe this is what you're asking, or
no? I'm just asking. You're using an MEV spacing to explain dark energy, but that is your only motivation. There's no other motivation that would give you a milli-electron volt spacing.
Yeah, no, it's just from dark energy. Yeah. So the dark energy density that we measured is just MEV. So then so this just gives you the spacing in the tower. Mm-hmm. Yes.
The question I have, I guess, what connection does this have to the Randall syndrome brain models? Like, should I view that as a specific case of this sort of?
You can. So this one is a flat extra dimension. You might be able. You probably can take a flat limit of, but
I mean,
but the connection is
because you would expect to have energy in the bulk and energy on the brain. And in that case, the spectrum looks totally different. But they're just assuming that there's no energy on the brain and no energy in the bulk, and it's flat. But that's just not the way things really work.
So, for example, in string theory, what you have like brains on oriented folks, they will cancel the energies. There's no such contribution.
Yeah, but the cosmological constant
depends on which kind of models one takes. But this is the assumption we made.
I mean, the problem is the cosmological constant is not determined just by the energy in the bulk here. It's determined by the cancellation of the energy on the brain and the energy in the bulk. So in general, you could get any cosmological constant.
No, I'm just talking about the warping effect. That's what I think.
I'm saying that the warping can be quite large, and you can still have small cosmological constant.
But I'm just saying in this model. I'm just saying what this model.
Yeah.
This model assumes that we have local cast.
Yeah. So I mean, so one thing I have to say, there's no UV. This is a cartoon of so we don't have a full UV construction of this. So I mean, I also won't use the higher dimensional picture at all. The only thing I'm going to rely on is that there is a tower as per the statement of the so there are potentially extra things and things to work out. So it's not like yes.
So maybe you don't want to go into that too much, but what is the initial condition which places us there in the context of early universe?
I mean, we don't know. So we don't know.
Is there an inflation? Is there somehow something, or I don't know whatever that creates this brain at some point?
It could be. So I mean, as far as what I'm saying is concerned, the only thing you need is that you start an initial condition where this is empty, the extra dimensions are empty, and the brain is hot. So how you get to that initial condition, I don't know. It could be inflation that reheats the brain. It could be something I don't know. But it's
And the brain has no localized energy density on it, is it?
It does. It has an energy density that's like T to the 4. It's hot. It's hot. It's just like it's
so I have students who are looking at the effect of that. It's not really a stable configuration.
Yes.
Did you say you need specifically one extra dimension? You said models are ruled out there.
Yeah. So there are okay. So there is there was a bound which people have corrected since, which says that if you have 2 extra dimensions or something, then the masses should be higher than KeV, then the KK mass should be higher than KeV. Since then, people have corrected that bound, so I don't know. So some analysis might need to be redone, and it's possible that you might have 2.
Well, but more than 2 certainly has been ruled out.
Yeah, more than 2 is
2
ruled.
dimensions gives you some bounds which are in conflict with BBN or borderline conflict with BBN. So there's that.
Yeah, well, so
the only option is that.
I mean, if you have 2 extra dimensions, then the universe could not have been much hotter than like 1 mega electron volt. So it's borderline okay with BBN, but also borderline not. And so, yeah. Okay. Any questions? Okay. Good. So the takeaways. So the details of this, many of the details we don't have, and the details of of these things will not be important for for what I say. The only thing that's going to be important is that dark matter could be these Kaluza-Klein particles that are that are in the tower, and in this case, the dark matter mass would depend on the size of the extra dimension. The dark matter mass is just inversely proportional to the size of the extra dimension. Okay, and so if the size of the extra dimension which is controlled by a field called the radion, if the size of the extra dimension were to change in cosmological history, then the dark matter mass would also change. Okay, good. Again, this is a higher dimensional sketch, but what we're going to be really thinking about is a system like this. So in 4 dimensions, yes.
Sorry, when you said the mass changes, are you also thinking the CC will change?
Yes, the CC will change because of V changes. Yeah, so there's one scalar field and V and the mass both depend on the same scalar field. So the CC will change too. Other questions? Okay, so this is like a higher dimensional, cartoon of what could be happening. But what we're really going to be doing is this. This is some effective 4-dimensional picture if you try to reduce to 4 dimensions. So in 4 dimensions, particle physics would look like this. There would be a standard model. This comes from the brain. There would be a tower of particles from the large extra dimension, and then there would be a large, there would be scalar fields that control the shape of this. Shape and size of this extra dimension, and these scalar fields, you get a number of them, but some of them could be massive, some of them could be stabilized, some of them could be rolling. We don't actually know. What we're going to do for phenomenology is take a combination of these and make is model dynamical dark energy by means of a combination of these scalar fields. Okay. Good. All right. So so that was the that was the model, and now we get to change gears a little bit and talk a little bit about the data, which was very beautifully. Yes.
What should we use these scalar fields to make a dynamical dark matter? The dark matter is the KK count, right?
Oh, I said dark energy as well. So dark energy will depend on some scalar field, and that scalar field you should think of as some linear combination of these scalar fields.
Yeah. What do I do with the other ones?
The other ones could be massive. They could have a potential that makes them massive.
But so, can you at the same time have the exponential potential you're using and mess up the other ones?
We don't have a UV model, so I cannot answer that.
But the hope is that
in concrete model. Yes, the hope is that this will be the case. Yeah. In the absence of a UV model, I can't answer most questions.
Sorry,
Uh,
could I ask,
yeah.
why isn't your radion, so you have an MEV radion, that's presumably coupled gravitationally?
Yeah.
But that's ruled out, right?
Sorry, this the radion is not MEV.
But they would need the radion to be MEV. If they wanted to have this dynamic, the radion would have to be MEV.
No, it would be Hubble. So it would be MEV is the lambda to the 1/4.
Yeah.
Would be lambda to the 1/2.
Oh, so you want this one. Okay.
Yeah, sorry. Yeah. Okay. So we can change gears a little bit and talk about the data, which was very nicely reviewed by Mustafa. So I won't have to say much, but okay. But let me give an overview. So there are some recent measurements that indicate a preference for dynamical dark energy over a cosmological constant, and so these appeared, in supernova data in 2024, but also, were emphasized much more in the DESI collaboration, over the past 2 years. So if you remember from Alex's talk, there is some. There were some arguments from theory that the cosmological constant should be dynamical to begin with, but Alec already reviewed these, so I'm not going to go into here. so instead, we're going to continue talking about the data. So the relevant data are the same data sets that we saw, over the previous talk, which is the CMB. So this is the cosmic microwave background. Then we have supernovae, and we have BAO measurements of DESI. And you can take various combinations of this data. And depending on which combinations you take, there is a different preference for dynamical dark energy. For example, if you take any two of the data sets, you find something like 2 to 3 sigma preference for dynamical dark energy. If you take all three together, it's at the level of 3 sigma. It used to be 3 to 4, but after the recalibration, it went back to 3. But it could be slightly above 3. It's like 3.3, 3.4 maybe. So just like we saw in the previous talk. Good. So this evidence is very often presented by means of this W0WA parameterization. So this W0WA parameterization is a parameterization for the dark energy equation of state, which is the ratio of the pressure to the energy density in dark energy. So W0WA means that you take a functional form for the dark energy equation of state, which looks like this. And then you say that the dark energy density is proportional to some integral of this function. Exponential of an integral of this function. Okay, and then you can try to fit the data and ask what are the parameters W0 and WA. If we had an exact cosmological constant, then W0 would be -1 and WA would be 0, and so you would be somewhere at this point here. So this plot actually we already saw in the previous talk, so I don't have to say much. But if we had a cosmological constant, then you would be somewhere here. But data prefers that W0 and WA are a bit far from this lambda CD endpoint by about 3 sigma. Okay. If you try to show if you try to study the actual equation of state implied by this fit, then the equation of state looks something like this, and so it starts at -0.8 or something, and then it dips below -1 at redshifts of about 0.5, and this feature is independent of parameterization and is present even if you do a bind fit, just like we saw in the previous talk. So this raises a small puzzle because usually scalar fields, so any scalar field with any potential, which is the typical way to model dynamical dark energy, any scalar field with any potential does not produce a W that is less than -1. The equation of state of a scalar field looks like this, and you can easily see that this is always between -1 and 1. For example, you can take the limit where the kinetic energy is negligible, then you get -1. You can take the limit where the potential energy is negligible, then you get 1, and everything else is in between. So then, one puzzle that was asked is how could you ever get an equation of state that is less than -1 when no scalar field with any potential you can dream of will produce
First on that, no theory in physics gives you that.
That's correct. That's correct.
Planets with no energy.
That's correct. It's actually believed that
it's just an example.
That's true. It's actually believed that that equations of state less than -1 violate the null energy condition, and so they are unstable. So the vacuum would be unstable.
Right, that's true only if it's forever less than -1, right? You can have something below -1 for a little bit.
Like a transient. Yeah.
But that's what you need here, right? You don't need it to be -1 forever, right?
Actually,
sorry, I mean, wouldn't that be like for instance, for a scalar field, like a ghost kinetic term?
Cannot be.
Even for a little bit for a
Cannot be a thing.
If you make your potential to have negative values, you can get -1 on that.
No, the potential can have any value.
Yeah, the potential can have any value.
Sorry?
You don't have a negative kinetic term.
Yeah. A transient behavior that's fixed later on, I don't know. Yeah, but then you're missing something. So if you should be able to fix it and find a theory that doesn't have that.
I was just referring to the null energy conditions are all about like time independent sense, right?
No, not necessarily.
It is true you can violate the null energy condition by short times and short opinions.
Yeah, that's what I'm saying.
Yeah. So that is true, but I think there's like a quantum effect. So cosmological time still seems kind of tricky. And in any case, like at classical level, I think it really requires.
Oh, I see. You think like Casimir or
Yeah.
You think Casimir's? Yeah, I see. Yeah, you can have Casimir's violent.
then there's an integrated version like the ANIC.
Right.
That one you cannot violate
Right,
at all.
right.
In quantum.
Yeah, point by point,
There's an average node
different than the average
node
node
of the universe.
is average.
Right. right. Okay. Yeah. So there's this feature of the fit to DESI CMB and and the supernovae data, which is that this effective equation of state seems to dip below -1. And in terms of an energy density, we saw also a version of this plot on the previous talk. So thank you, Mustafa. You made my life very easy. Like, so in terms of the energy density, if you plot the energy density implied by that equation of state in dark energy, it looks like the energy density goes up and then goes back down. And it's this going up behavior that is tricky to model in a universe that is expanding. So when things are expanding, you would imagine energy densities to decrease, not increase like this. Okay, or at best, like worst case scenario, they stay constant if it's a cosmological constant, but otherwise they should decrease. That's the same statement. Okay, good. So data seems to have a preference for dynamical dark energy, and so we want in order to model this preference, in the context of this dark dimension scenario, we will take. I mentioned earlier that we have a collection of these fields. We can take a linear combination of these fields, and let's call it phi, and let's study this one linear combination of these fields, and this is not special. So everybody models dynamical dark energy by means of a rolling scalar field. But then, in the context of these models, you should ask what physical quantities can depend on phi, because if the scalar field were to roll, then you would change the properties of this internal manifold, and then some physical quantities could easily depend on phi. So they could easily depend on the value of phi. It turns out we have very strong constraints on things in the visible sector. So we have very strong constraints on couplings at the standard model, masses in the standard model, and so on. And so you would not be able to change any couplings or masses within the standard model in a way that is consistent with cosmology and not run into bounds from other experiments. So experiments that measure variations of defined structure constant or something like that. It would be hard to do that. On the other hand, there aren't really that strong constraints on dark sector quantities, and in particular, there aren't strong constraints on the masses of dark matter, and we saw that in this model, it's if the length of the extra dimension were to change, then very naturally the mass of the dark matter would change. Yeah, in fact, it could change, but it seems like data does prefer it to change. But let me say one more sentence about this. So recall that the mass was linked to the cosmological constant. And so if you imagine that the cosmological constant is changing, then you should also imagine that the masses of dark matter is changing. Okay, this is another way to say what the things that I said on the previous slide. There is a relation between them in the context of the dark dimension, and so once one changes, you should also imagine that the other should be changing too. And then so we can take we don't have a UV model, but we can take the simplest effective description of this behavior, which is that locally we say that the potential is exponential with some exponent c. And locally, we say that the mass is exponential with some exponent c prime. Okay, this isn't supposed to be a global functional form for V or M, but it's just supposed to hold locally and apply to whatever field range we are talking about, which will be small. It's smaller than M plane. Okay, so this is the model that I started
with one important restriction on CNC prime.
With one important restriction.
Otherwise, you're not saying anything.
Sorry, what's the
If you just said you have just a function, you just think, but there's crucial fact that CNC prime of order 1. This is a crucial.
Oh, CNC prime of order 1. Yes, okay.
Very important. Otherwise, anybody's model.
Yes, I see. Yes, with CNC prime of order 1. Okay. So this model actually we already analyzed back in 2019, way before the DESI data was out, and it was motivated in exactly the same way that I motivated this for you now, which is that the cosmological constant is small. You would imagine there's a tower that could be the dark matter, and so the dark matter mass would be linked somehow to the value of the cosmological constant. Okay. The only difference, so we did basically the same analysis. The only difference is that back in 2019 we had C and C prime always be of the same sign. Now we have C and C prime; they can be of opposite signs. That's basically the major technical change between both. Yes.
Can I ask maybe a light question and maybe we'll get to it. Shouldn't this be like if the mass of the dark matter is changing and you have multiple fields that as Hubble is decreasing, you have multiple fields that are switching to behave like dark matter, as in they're starting to oscillate in their potential. But because earlier they were frozen, and as Hubble decreases, more and more fields are behaving like dark matter instead of dark energy, right?
No, so it's not like that because all of these fields are heavy compared to Hubble always. So the whole tower is heavy. So the things that make up dark matter are not. Yeah, which fields?
I think the point of confusion, if I understand correctly, is that when you mentioned multiple phis, I think you should have said that there's only one phi, which is massless combination.
Yes.
I think that's his confusion. Is that he's saying they become massless, these other phis.
You asking about the phis or the dark matter particles?
Well, I thought some of the phis were your dark matter particles. You
No,
have a
no,
tower
no,
of phis.
no, no,
Oh,
no.
okay.
There's
no condensation.
yeah. So
there is some dark matter whose mass is controlled by phi. That's it. The phi itself is not a dark
I
matter.
confused. You should just have one phi.
this phi
The combination
sounds
that's your
good.
role.
Okay, sounds good. So there's only we're going to focus on only one combination. Everything is massive. All of these are massive. And the dark matter is made up of this tower, which are the Kaluza-Klein states. So the phis control the shape and size of this extra dimension. Yeah. Okay, good. What else was I going to say? Yeah. So by convention we take C prime to be always positive, so that if you have a scalar field and we plot the dependence of the mass on that scalar field, then it's always a falling function, just like this blue curve. The fact that C can be positive or negative means that the potential means that you could be on this side of a bump in the potential or on this side of a bump in the potential. Okay, so the potential can have a bump, and then if you are to the right of it, then C and C prime are both positive, but if you are to the left of it, then C and C prime are of opposite sign. Okay, good. Okay, so that is the model. Then we do what is done for the W0 WA parameterization, which is that we take this model and we fit the data. Okay. Okay, so there are two cases we can consider, which is that C and C prime are of opposite sign or C and C prime are of the same sign. It turns out that the ones where they are of the opposite sign provides a slightly better fit to data. So here, so here I'm showing you the fit compared to the W0 WA parameterization, which we already discussed. So these numbers are not yet updated with the recalibrated supernovae samples, except for the last one. So the last line is up to date, and is representative of the other supernovae samples. So you can, if you want, just focus on the last line here. You can see that W0 WA is preferred at some 3.1 sigma significance, and that the model that I just described has the same or maybe even slightly better preference under this supernova sample. This is the recalibration of the DESI 5. Yeah.
And the extra parameters are like each model has 2 additional parameters. Is
The
that
same
right?
number of extra parameters. Yeah. So WWA has 2 extra parameters. Yeah, that's counted in here. It's counted in the significance. Yeah. Okay. So this model you can check, actually, even you can think of these as mock data if you want, but they are real data. But you can check that you can reproduce actually the significance of W0 WA for all of the data sets. And as far as we know, this is the only model in the literature that can actually, the only physical model in the literature that can actually reproduce a significance given by W0 WA. Okay. So all other models, including things like axions or spatial curvature, they are preferred at a slightly lower significance, than this coupled dark energy, dark matter model. Okay. Yes.
Am I correct? It looks like you have to have the tower of massive particles to get agreement. Is that right? Like if you imagine that you just had the exponential potential, then that alone wouldn't work.
I think so. If you're just looking for the fit, like for a phenofit, you can get rid of the tower and just put a massive particle whose mass depends on phi.
No,
That-
he asked a different question. He said if the mass did not, but that's what your question was.
Yeah, I'm saying,
No,
don't have the
tower
massive
extension.
particles at all, don't have the tower, just have a a field rolling in a potential.
Yeah.
In an exponential potential.
Oh,
not phi.
oh,
Talking about quintessence.
Yeah.
oh, I see. No, yeah. So that wouldn't fit. So that's the case where C prime is 0.
Yeah, yeah.
That's the case where C prime is 0. So the C prime 0 is actually not preferred by the fit. Yeah. Yeah, I see. That's it. Thanks. Yes.
So with the varying dark energy and dark matter, does it give you the equation of state? I mean, how does it give you
Yes.
the negative?
I will show you that in a moment. Yeah.
And the fits to different data sets are consistent because there are different values of C and C prime at a canopy. They are consistent.
Yeah. This was part of the thing I was going to emphasize on the next slide, but thank you. So this is so here everything basically gives you the same value of C prime. It's 0.05. These I will show you. So I can show you now. So with the recalibrated, I don't have the numbers, but we do have the MCMCs. So with the recalibrated supernovae samples, all these measurements for C and C prime are, they all give you the same number. So it's a very similar story to what we heard in the
It was
previous
not
one.
consistent before the recalibration.
No, it was not.
Yes.
So we could have predicted some recalibration is needed. So yeah.
So now the interesting is that the first one, the dark blue one, does not include even supernova.
Yes.
It's just CMB and this.
Yeah, the first one does not include sorry, maybe you cannot read from the back, but this is the first one is just CMB and DESI, and all of these they have the supernovae samples. It's Union, Pantene Plus, and DES with this Dufke recalibration. Good. Okay, so a few things I want to mention. Yeah, so this I mentioned, and and this I mentioned. Okay. Yeah, let me make a few comments about this. So we can go back to this. So notice that the exponents that we get from here, for example, are around -1 and 0.05. Or you can look here, it's around -1 or -0.8 or -1 and 0.05. But the recalibrated ones are all around -1. These numbers are much too small to satisfy the numbers that Alec mentioned, which we know are the correct bounds for C and C prime in the asymptotics of field space. So, from Alec's talk, you might remember this number √2 and 1/√2, which is 1.4 and 0.7. And if we were in the asymptotics of of moduli space, then C would have to be bigger than 1.4, but the C that we find is -1, so it's smaller than, in absolute value, it's smaller than 1.4. And C prime would have to be 0.7, but this is 0.05, so we are not really in the asymptotics in some sense. So so these numbers don't satisfy these asymptotic bounds. On the other hand, this number, if you remember, what I forgot to put it here, but there's a bound from the TCC for the interior of moduli space, which is around 0.8. That was the 2/√d - 1 d - 2 that evaluates to about 0.8. And these numbers do satisfy the 0.8 value. So this is -1, which is bigger than 0.8. So it's consistent with the statement of TCC. Good. Okay. So sorry, there's a typo here. So then we have. Oh no, the slides are out of order. Yeah, sorry. There's a missing slide. So there's a similar story for C positive. So this should be C positive. So I told you C and C prime can be of the same or opposite signs. I just mentioned the story where they are of opposite signs. There's a similar story where where C is of the same sign, and again with the recalibration, there's some consistent measurement of C, and there's a consistent measurement of C prime. The preference for this is slightly lower than the preference of the opposite sign case. But not by much. So by about 0 to ½ a sigma. So depending on by like point few sigma. Good. Okay. Let me mention a few other things. So you can try. Sorry, these spots might be too small to be seen from the back, but I will explain them. So it seems like if you combine CMB and DESI and you leave the supernovae outside of this fit, so you exclude the supernovae, then what you get is something like this. And this you can see, so this is the distribution for C. So C actually is consistent with 0 in this, in this plot, but C prime is not consistent with 0. So most of the preference for CMB and DESI is actually for a non-zero C prime instead of a non-zero C. So in this sense, DESI and the CMB, they prefer a varying dark matter mass more than they prefer a dynamical dark energy. Okay. And this is one way you can understand the tension between the matter densities measured between the CMB and DESI. They measure different matter densities, and you can accommodate that by just having a non-zero C prime, and you can just leave the dark energy alone. You can have the dark energy be a cosmological constant. On the other hand, for the supernovae, the story is reversed. So if you exclude DESI, so all these data sets exclude DESI, so that is CMB, the gray one is CMB alone, and then every other color thing is CMB plus one of the supernovae data sets. And if you exclude DESI, then the conclusion is the opposite, which is that there is no preference for C prime, so C prime is consistent with 0. But there is a non-zero, measured value of C. So there's a preference for non-zero C, but no preference for non-zero C prime.
This plot is before recalibration.
This plot is before the recalibration. Yes. Yeah. Sorry about that. Yeah. So the but I don't think the recalibration changes. Yeah. So the conclusion. Yeah. So it seems like CMB plus the supernovae, they prefer a varying dark energy density, and then at least in the context of this model, and CMB and DESI they are consistent with 0 C but non-zero C prime.
Because it's DESI that is pulling omega matter to be lower.
Yeah, exactly. So the CMB wants some matter density, and then DESI wants a different thing, but you can fit that better somehow by changing C prime but leaving C to 0, and then yeah.
I was just wondering, so
Yeah.
what kind of priors boundaries are you putting on the C and C prime when you vary your chains, when you run your chains?
They're flat and they're big. They're much bigger than the range that we're plotting here. So this is like, I don't know, it goes to minus 2, minus 3, probably. Yeah.
So the stop there at minus 1.5. So it's really coming from the data. There is no.
There's no hard
prior
prior.
stop.
No. Yeah, we're not hitting the prior. I mean, we're hitting the prior in this CMB thing, but that's not, the CMB alone doesn't have a preference for any. Yeah. Okay.
Those priors came from the arguments that Alec was reviewing. So C and C prime order 1 is what is, I think, the distinguishing factor of this model, which is precisely that range.
Sure.
That
Yeah.
range.
Yes. Yeah. In particular, I was kind of curious to see. So you have this kind of horizontal band going there for C prime,
Mhm.
and I saw it also in the previous slide, and I was just wondering.
Sorry,
Yeah, earlier, it's okay. It's practically the same. So yeah, we see the blue there.
Right.
It's not that it's a problem or anything. I'm just curious to know. So you can kind of constrain it on this side, and then you're not constraining it on that side when you use just DESI plus CMB.
Right.
That's
Exactly.
keeping it prior, no?
It's
At 0, you're putting a prior.
Yeah. So this is just saying that like C and C prime are of opposite signs. So
Yeah, but
Yeah.
C there is negative, so it is hitting the 0.
yes, but then we have the other one, which is also where it's positive, and it hits 0 again.
That's
So so you could combine both. You can stick both of them together, and then there would be one. Yeah, it's just consistent with 0 in both pictures. Yes.
So usually these moduli, they come exponentially decaying.
Yeah.
So how would you be able to get C to be negative? Is it hard to make it be negative?
Yeah. So negative is like it happens because of like this. So let's say by convention we take C prime to be positive, and if the potential has a bump, then C being negative or positive is just a question of whether you are to the left of the bump or to the right of the bump. And so if you have a bump in the potential, which there are examples that people wrote about in the past a couple of years, then if you are to the left of the bump, it would look like they have opposite sign. If you are to the right of the bump, it would look like they have the same sign.
Can the left of the bump ever be in a weakly coupled region of moduli space?
I mean, Yeah, the hope is yes. I don't know for sure. So it's yeah, I think is yeah. Okay. Any questions? Okay. Okay. So now we can yeah. So this is all. These comments I made. So the case for when C is positive. So this has a similar significance to the case where C is negative. There's a slightly higher preference for the case where C and C prime are of opposite sign, but you can compare here for the supernovae before the recalibration. You can see it's not really that different, like 2.6, 2.7. This one is a bit more different, but it's like half a sigma off between the two of them. Good. So next we move on to the explanation of this phantom behavior, and like I mentioned before, so the fitting the data gives you an equation of state for dark energy that seems to go phantom at a redshift of about a half. Okay, but in all these fits, it was assumed that dark energy and dark matter were decoupled, so that the dark matter density redshifts exactly like 1/a cubed. So it's it's an observation that was made before I guess like yeah and on various occasions people have made this observation that you may actually infer that the equation of state of dark energy is less than -1 if the dark energy and the dark matter are coupled, but then you neglect this coupling when you are trying to fit data. So the way this works is that let's assume that dark energy and dark matter are coupled, so they form one fluid together. And let's say that this fluid somehow is able to exchange energy between dark energy and dark matter, so that the total fluid redshifts slower than what it would have done if they weren't coupled. Okay, if the total fluid redshifts slower, and you assume that the dark matter has an equation of state that's 0, then the only way you can get the total fluid to redshift slower is if the dark energy redshifts with W smaller than -1. That's the only way you can make the total combined fluid redshift slower than it would have done in the uncoupled case. Okay, and so what's happening in this model that I'm showing you is exactly this effect, which is that if you say I'm going to call dark matter the thing that redshifts like 1/a cubed, so it has W exactly 0. Then the coupling between the two, and in this model, the total combined fluid redshifts slower than the combined fluid in lambda CDM. So then you can plot an effective equation of state for this model, and it looks something like this. So if you plot an effective equation of state for this model, it would look very similar to the equation of state that we saw for the DESI fits. This effective equation of state is defined like this. So let's say that so the model has two things. It has a scalar field and dark matter, and let's say these are the energy densities and pressures for both the scalar field and dark matter, and let's say that I want to insist that the dark matter energy density redshifts like 1/a cubed. So in real life, this is not true. The dark matter energy density redshifts like 1/a cubed times e to the minus c prime phi. If phi were to change, then the dark matter density would change. Yes.
Oh, yeah. I guess that was going to be my question. You can't assume that rho goes as 1/a cubed, right? Because the mass of the dark matter is changing, so the effective equation of state is different.
Yeah, so there's some combined fluid. We have no way of disentangling them in experiment. So what I can do is I can assume that this goes like 1/a cubed, and then add and subtract that difference.
You just, okay.
Yeah.
Okay.
So I'm reshuffling them. I'm reshuffling what you're calling.
Okay.
So in the DESI papers, if you read the DESI papers, when they do a fit, there is this assumption that the dark matter density goes like 1/a cubed. And so there's implicitly also this assumption that you are adding and subtracting something to the dark energy density. Okay, the pressures are standard, so dark matter is pressureless, but the pressure of the scalar field is just this, like we saw earlier. Now you can define an effective equation of state for this dark energy, which is the dark energy that is being fit for, and this equation of state is just the ratio of the pressure to the energy density. But if you do this, you'll find that it's the same W phi that we saw, a few slides ago now. So this is the equation of state of a scalar field with a potential, but with this correction in the denominator, 1 plus x, and x happens to be negative because x is proportional to this quantity. So once phi becomes anything bigger than 0, then this quantity is negative and x is negative. So you can see now that this effective equation of state can actually dip below -1. If W phi is close to -1 and X is negative, then the ratio can be smaller than -1. Yes?
Would you have to include the back reaction on phi because you're changing the dark matter and dark energy density, which would introduce additional phi potential? So
Yes.
they might not want to go in a direction where it's making.
I mean, we include that. So there is, so you, I mean, we include that. So the dark matter is part of the potential for phi. That's not what you're asking, no?
I didn't, so you're saying that, so you're not just having the phi roll, you're actually including the fact that there's back reaction.
Yeah, yeah, yeah.
From
We
the
include
fact
that. So
that you're changing-
the dark matter is contributes a potential to phi.
It's going to be important for that.
Yeah, yeah. It's actually very important for this to happen. Yeah.
You're going to say about shift.
I don't think so because I'm out of time, but but I can say it afterwards in question. Any other questions?
The perturbations in this coupled dark matter, dark energy fluid.
Yes, yes. So this is we do a full class simulation. So we derive the perturbation equations and put them in class. So the MCMCs that I was showing you were full with perturbations included.
Is there an instability on large scales?
I don't think so. What sort of instability?
Other perturbations in this combined fluid grow with time at large scales.
I don't think so. I don't think we've seen anything like that. But yeah, but we should talk after maybe. Yeah.
This, I don't know, this may behave like an somehow like an interacting, if that's the case, an interacting dark energy, dark matter fluids, and there are also perturbations where there is no instability. There are no instability. So it's, I mean, it's a good thing to check. I mean,
So what sort of instability are you thinking? Like forming structures on large scales, or yeah? I'm not sure, but they cannot. I don't think there's a fundamental instability because we start with like a theory with a healthy Lagrangian. So, but maybe by instability you mean something else, like a cosmological formation of a large structure.
Quintessence models have a negative W, but they're stable because there's an energy density, an energy penalty for a density gradient. More generally, fluids that have W negative have instabilities.
Yeah,
and here you have dark matter coupled to, it's sort of like a chameleon thing.
But this wouldn't have that. So I think the instabilities you're talking about are actually fundamental instabilities. So they're not just cosmological. But this wouldn't have that because the theory is actually, it satisfies the null energy condition. So for these instabilities, these are very similar to the instabilities that Miguel was mentioning, which is that theories that violate the null energy condition, if you were to change the sign of the kinetic term, for example, these would have instabilities of the type.
It's not it's like in chameleon theories, you've got a scalar field.
Yeah.
It's coupled to a mass, or like same thing with mass bearing neutrinos.
Right.
That was a model where you had a quintessence field coupled to a neutrino. As the neutrino mass was fixed by the value of the quintessence field. And so you could get W less than -1, but if you actually analyze perturbations, then the perturbation, density perturbations.
Yeah, but W is not so much.
Yeah, this W is not less than I don't know. So this W effective is definition dependent. So I don't think this W effective is anything physical because it depends on my subtracting and adding of things in a special way. If I were to subtract and add different things, I would get. So this W is not actually something that can signal an instability. This W might, but this W is always good. This W is always above -1. So yeah, we should maybe take. I think I'm running out of time, but
okay.
There's
I have a comment related to that, but we can talk later.
Yes, maybe we should. Okay. Okay, good. And so if you were to plot the behavior of this, dark energy density, I mean this dark energy density, so the one that's not really just a scalar field, but also with the correction, then you would get something that looks very similar to the curve that was, that we saw from the DESI data. So something that goes up and then goes back down, and yeah, it's qualitatively very similar.
So that means that the energy transfer between dark matter and dark energies, it happens in both ways.
Yeah. So it could potentially happen both ways. Yeah. Yeah, at some point the dark matter could be pushing the dark energy field, and at other points then it could be taking energy from it. So the dark matter mass, for example, in the case where C and C prime are of opposite sign, it decreases and then increases a little bit afterwards. So this is the both ways transfer of energy. Yeah, that's correct. Okay. Finally, there are if you believe this value of of C prime that we measured, then there's actually a fifth force in the dark sector from the exchange of this little phi particle. And we can compute, so for the value of C prime that we found, so C prime is 0.05. For the value of C prime that we found, we can compute the strength of this fifth force relative to gravity, and it's about 0.5%. Okay. There are bounds on these, fifth forces in the dark sector. One of the bounds is, is by Mark and Geston, and so in this bound they find that the force of gravity, the fifth force compared to the force of gravity has to be less than 9%, which translates to a C value of about 0.2. So these two numbers you can see are consistent. This is about a factor of 20. Less than this. But in principle, if you could do, for example, better measurements, then you could detect this fifth force in some independent way, in a way that has nothing to do with the DESI data. So this is some prediction that you can use to verify or rule out this model independently from cosmology. Okay, so I'm out of time. Sorry for going a bit over time, but this is the summary. So we use some motivation and recent observations, and we study the model with a potential that is exponential and a dark matter mass that's also exponential. And we saw that this model has some preference, over this has some preference over lambda CDM by up to, sorry, this should be 3.4. Good. And so this model makes a prediction for a fifth force in the dark sector that could be verified, and it raises other questions as to what else could be varying, what else could depend on this phi, and there are various other interesting things to do in the context of this. Thank you so much for listening, and